Let's work through some examples from 5.4. So one of the biggest things in 5.4 you need to get is how the different properties work. So one of our properties is that if we have log of a product, we can express that as a sum of logarithms. Log of one factor plus log of another factor. And this can go on regardless of how many factors we have. If we have 3 factors in there, we can add 3 logs together, or we take the log of each factor. So one of the ones that I pulled up from homework is log base 6 of 13z. So keep in mind what 13z means. 13z means 13 times z. So we can express this as the log of 13 and the log of z. So log base 6 of 13, log base 6 of z, and those get added together. So this is just one of the properties of logarithms. We have to be careful. Occasionally we'll have a sum on the inside, like x plus 5. We do not have a property to express this as separate logs. So that doesn't break down any farther. But if we have a product in here, we can break that into separate logarithms. So let's try and take a look at another one. Let's do log base 7 of 5 over k. So like if we have a product, we can take the log of each piece. We can also do that if we have a quotient. So we can take log of the numerator, log of the denominator, and subtract those. Whichever factor is in the denominator, when we take log of it, that term is negative. Whichever term is in the numerator, when we take log of it, that one's positive. And we have to make sure whatever our base is here, we include the same bases for our new logarithms. So another homework problem deals with having something raised to a power. So if we have something to a power, we have a rule that allows us to bring our exponent out front and rewrite this as 5 times log of x. All right. So let's suppose we have log base b of x to the 8th, y to the 3rd, z. And we want to write this as sums and differences. Then since these are all multiplied, we take the log of each factor, so the log of x to the 8th, log of y to the 3rd, log of z. Since there are none in the denominator, none of these terms are going to be negative, so each term is positive. One other thing that we can do is notice we have exponents there and exponents there. So we're able to bring our exponents out front and call this 8 log base b of x plus 3 log base b of y plus log base b of z. If we had a number for the base, and if these were numbers and they could be simplified, then we would want to do so. But as this is, we can't break this down any farther. So let's do one that involves a quotient. Let's suppose we have log base b of p to the 3rd, m to the 2nd, n to the 5th, over x to the 3rd, y to the 7th. So let's express this as sums and or differences of logarithms. So we have factors on top, factors on the bottom, so we can take the log of each factor. The p cubed, the m squared, the n to the 5th, the x cubed, and the y to the 7th. Each of those we're taking log using base b, taking log of each of those factors. All of the ones that are on top, those terms are going to be positive. The ones that are in the denominator, those terms are going to be negative. And if you watch the video from my math lab that went with this section, then they should have introduced that property. So the other thing we can do is we can bring our exponents out front. So this 3 we can bring in front of the first term. This 2 can be brought in front of its term. So can the 5. So can the 3 and the 7. Let's work through one that has a radical. Let's do log base d of the square root of x to the 5th over d to the 3rd, c to the 4th. And let's make sure that this square root is over all of that, not just part of it. So we can do this a couple of different ways. First, we want to convert the radical to an exponent instead of leaving it as a radical. We could call this entire piece to the 1/2 power. We could call this x to the 5th over d cubed c to the 4th, and that's to the 1/2 power. And then we could bring that exponent out front. Now, we have to be careful if we do it that way, because when we bring that 1/2 in front of our logarithm, whatever we do to rewrite that part, that 1/2 is multiplied times all of it. So if we rewrite that as 2 or 3 different terms, each one of those gets multiplied by 1/2. And that's fine to do it that way if you prefer. Another way we can do is to go ahead and distribute this 1/2 before we split it up. Remember, when we have a fraction and we have products and that's raised to a power, each factor gets that exponent. So this part gets that exponent, and how do we do that? If we have x to the 5th raised to the 1/2 power, a power raised to a power, we multiply the exponents. So on top, that would give us x to the 5/2. On bottom, when we do this one to the 1/2, we're going to do 3 times 1/2, so 3/2. And on bottom, when we do this one to the 1/2, we're going to do 4 times 1/2, which is 2. So now that we have taken care of our exponent, now we can break this apart. So we do log of the numerator, log of the piece that has a d, log of c. The term on top, or the 1 on top, that term is positive. The factors on bottom, those terms are negative. So now we can do a little bit more to simplify. For the first one, we can bring a 5/2 out front. For this one, we have a property that if our base here and our base here are the same, essentially those undo each other, leaving us just the exponent. You could also see that as if you bring the x out front, if this and this are the same, well, what exponent does this need to get to make that? Well, a 1. A to the first power makes a. So that would equal 1. So we would get x. But it's best to just use the property that if you have this base and that base are the same, those cancel, leaving the exponent. So here, this base and that base are the same, so that leaves us minus 3/2. These bases are not the same, so they don't cancel each other out. So we leave that like this. Let's do a couple more. So it's possible that we might be given a list of logs and asked to write this as a single logarithm. And let's not put exponents on there. Let's put numbers in front. Let's make this one minus, like that. So our product and our quotient rule that we looked at earlier, when we have a product and we said we could take the log of each factor, these two sides are equivalent. In the past, we went from this side to that side, but we can go from this side to that side just as easily. One thing we have to be careful with is that the coefficient here is 1 and the coefficient here is 1. If there are other numbers in front, then we can't make a direct transition. So what we have to do on a problem like this is we have to get rid of the coefficients. So this coefficient we can move up as an exponent. This coefficient we can move up as an exponent. And so can we with that one. Now that each coefficient is 1, we can express this as a single log. The terms that are positive, those inside pieces go as factors on top. The term that's negative, that goes as a factor on the bottom. Like that. So then we might be given something such as log base B of 7 equals 1.946, and log base B of 9 equals 2.197. So suppose that we need to find log base B of 63. Well, we don't know what this base is, so we can't just simply use our calculator and the change of base formula to evaluate it. What we do know is that 63 is 7 times 9. And if we have a product here, we're able to write this as log of 7 plus log of 9. We know how much log of 7 is. We know how much log of 9 is. So we can add those together. 1.946 plus 2.197, and that's our answer. So this is just a selection of different problems going over properties of logarithms.